Hi, I'm Audrey Girouard, and this is work done in collaboration with Pietrzak and my now graduated student, Nick Fellion. So I'm very excited to talk to you about it. So in physical art, an artist can manipulate a wide variety of parameters simultaneously in addition to the path of the drawing tool. They can manipulate the angle of the nib, the tilt of the brush, the amount of pressure that's applied. Augmented styluses are meant to provide more control and precision on tablets, not only for the XY position, but usually an additional parameter, mainly pressure in commercial devices like here, where you can change the thickness of the brush. But pressure is not adequate enough to reproduce physical artistic tools. In addition to pressure, researchers have looked into roll and tilt to augment these things, and as well looked at how we hold our devices, so different stylus grips. Whether you're writing, you're sketching, and if you're painting, you're going to hold your stylus differently. And that can lead to applying different, knowing what context it's in. For example, with the Conte project, where you can sketch if you hold it one way, or you can have a menu if you hold it another way. So this work is also using previous work in deformation. So we have two classic deformable devices on the left, which are gummy and paper phone, and those are flat slate devices, and that's really the form factor of most deformable devices that researchers have put together. And that is partly due to the fact that they use thin film resisting sensors, whether printed in the lab or commercial ones. They're very easy and accessible and cheap to use. And so that kind of explains a little bit of the form factor. Now, there's been a few other deformable devices that have a different form factor. For example, we have Shape Tape on the side, which uses fiber-optic sensing. And here comes our own device, which is called FlexStylus. And it's meant to help digital artists that want a richer amount of parameters. And so FlexStylus is a flexible stylus. It detects deformation of the barrel of the stylus, where sort of on the portion on the left here. It provides 2 degrees of freedom to improve the expressivity of digital art using a flexible stylus. So we use the technology, the sensing technology of fiber-optic cables. And the basic principle of this is you can take a fiber-optic cable, you abrade it, you kind of cut a little thin slice out of it on the side. And if you put an LED to it and you shine light, what happens is that if the cable is flat, then the light can come up at the other end. However, when you bend it in the direction opposite to where it's abraded, light is going to come off. So if you measure the amount of light at the other end, you're going to have a lower amount. So you have a one-directional bend sensor with this. We combined it, 4 of those together, and then you can get an idea of how it's bent in a 360 manner. So our prototype has a conductive nib at one end so that you can still use it as a basic stylus. We're using an IR LED in the tip, combined with 4 fiber-optic cables and surface mount phototransistor at the other end to measure the amount of light that's dispersed. We have about a 4-centimeter section that bends, and that's evolved with our prototypes to reducing it to this. We realized that's where people were mainly bending it. It protects the sensors for the rest of it, so it lasts a little longer as well. And what we measure is both the absolute deformation, sort of how far from straight this is, and as well the direction that you're bending it into. And here is us doing a circle with the tip of the sensor, and you can see the 4 data streams for our 4 fiber optic cables. as we're doing this. So, of course, we have a nice piece of technology. We wanted to think about what type of interaction techniques we can do with this. And as we were developing them, we realized that they were all based on different grips. And so we concentrate on 3 specific grips. There might be more, but we looked at the tool grip, which is how you would hold a pen if you were writing, the menu grip, which has the nib on the tablet, but you're holding it from up top. And then if you're just holding a pen in your hand and then you manipulate it, that's an in-air grip. So most control over the XY position with the tool grip, and then most control over the bending, both the angle and the amount of bending with the in-air grip. So what does our tool grip give us? Mainly, that's augmented drawing, meaning that you can control the X and Y position, but as you're doing this, you can use your thumb and your index to push on the pen and bend it, and that gives you another set of input. Here, I'm changing the hue from black to red, depending on the amount of bending, and I've got a video illustrating the size of the brush here. As you're bending, then the brush becomes larger. In the menu grip, meaning that the stylus is on the tablet but you're holding it from up top, this allows you to use it as a secondary pointer. So we have a radial menu, selection, interaction, and then we can simply do gestures that can lead to certain actions. So for the radial menu, you can see that because we have, we're controlling both the direction and the amount of bending, we get this secondary pointer which can be used to select a specific option, and then once we cross it, then it actually makes the selection. For our 2D color wheel, well, once you position it using the same principle of the secondary pointer, selection is not something that you can use for crossing, so we just added a button to make the selection. So here you could go from picking colors of red to blue, and this can be the colors that you use for your augmented drawing to go from one color to the next. We have the in-air grip, where you're basically holding it without any support, without touching the tablet. And as you're bending it, you can essentially roll it in your fingers, and that can lead to navigation. So you can scroll the document and decide the direction of the scroll and how fast you're navigating it through, how much you're bending and how fast you're rolling it. So to evaluate how interesting FlexStylus was, we focused on comparing absolute bending, so one of the 2 degrees of freedom, to pressure. So we picked absolute bending because it is the most similar to pressure, pressure being the most commonly used commercially available augmentation for styluses. And both are defined as a distance from a neutral resting state, so we thought they would be a good comparison. And we compared it to a Surface Pro pen because we wanted a stylus that works on normal type of tablet. So our task is matching a function that's displayed. So we have the black function, and as the user is increasing the input, whether pressure or bend, then this creates the gray line that you can see overlaid. So I have an example here. We start with pressure, and they're trying to match the black curve. And now we have the bend input example. So we have a 2x3x3 within subject study, 2 different types of input methods. We tested also 3 different types of function, a square function, a triangular function, and a sine function. And for each of those, we had 3 different sizes, small, medium, large. We had 18 right-handed participants, and the tasks were counterbalanced. So we first thought that FlexStylus will be more precise than bend input. That's partly due to the fact that the distance traveled when you're pressing a stylus is about 1 millimeter, so it's quite short, so it's hard to control. It can be hard to control. And bending it gives you a little bit more amount of physical space, more like in the 1 centimeter range. We also saw that because pressure has more control when you're pressing down than when you're releasing it, we thought that FlexStylus would be better at that. So it would be more control when you're releasing, so going from high input to low input. And that for both types of input, a smaller change would lead to higher accuracy. So when we compare the overall distance from the target, so the gray versus the black line, FlexStylus was more accurate overall. However, there was no interaction effects between function type or target size. So it's in general situations, not for any specific ones. We also wanted to look at the bidirectionality. Is there a difference when you're increasing the input versus releasing it? So we took the data from our triangle and our sine function, and we broke it down to whether you're increasing it or decreasing it. And we found that overall, users are more precise when increasing the input than decreasing it, but there's no interaction effect with the type of input. Then we looked at the different accuracy when it came to being static or dynamic, and we used the square function for this. For the static accuracy, we looked at all the flat surfaces here in orange, and we found no significant results between input. So overall, for both the pressure and the FlexStylus, users are approximately as precise when keeping a certain amount of input. We looked at the dynamic accuracy, and that's when there's a big jump, essentially going from a low flat surface to a high flat surface in a very short amount of time. As distance of travel increases, we found that the accuracy decreases because we had some small jumps and some bigger jumps. But again, no significant results between inputs. We asked our participants what they thought of our FlexStylus, how comfortable it was to use, what their perceived accuracy was. And they thought it was, it was their stylus of choice when it came to perceived accuracy. They were more balanced in terms of what was comfortable. Of course, what's interesting here is that you're comparing a commercially available stylus versus our prototype, which is not perfect. And so overall, we think there's a lot of interesting data here because they still preferred our stylus overall. So what we found is that FlexStylus is more precise than pressure input. However, it behaves similarly when it came to releasing the input. So we think that the larger motion and real space associated with FlexStylus really gives them the additional control. And there's the inherent haptic and tactile feedback to the fact that you're bending it and you know how far you're bending it. That is giving our users the added advantage and the added control for this. So what we created here is we developed FlexStylus, an augmented stylus that gives 2 degrees of freedom, two additional degrees of freedom to users. We created 8 interaction techniques based on 3 different grips. We compared it to pressure. We found it was more precise. Future work, as usual, involves refining the physical prototype and running studies that include both the absolute bending and the rotational bending for this. And I'm looking for a postdoc to continue this work, so come talk to me if you're interested or if you know somebody that's interested. Thank you.
Hi, Gonzalo Ramos, Microsoft Research. Lovely work. I didn't have a chance to look into it when I was working on this, but you may want to look into the difference between being good at exerting force and decreasing force. Is rooted in the mechanoreceptor nature that we have, and the just noticeable differences levels that occur when you're accustomed to have high force applied, and then suddenly you have to decrease it, versus low force, and then you have to increase it. just a point to the future directions to look into why you're observing what you're observing.
Yes, that's a good point. Thank you.
Other question?
Yeah.
Andy Wilson, Microsoft Research. So you showed some footage of painting in the beginning, and there the deformation is really at the tip of the brush, right?
Yeah.
And then you show a device where the flex is really sort of in the middle of the device, and I was wondering if that, but you didn't really talk about like why you put it there, and I'm wondering if that was a kind of a thing as a compromise in sort of the technology, if you would rather have the deformation at the tip, or if you just say a few words about the position of the flex, because I think that's very important in this device. It sort of constrains what you can do with it.
Yes, you're right. Right now we need sort of the LED to be at the tip, or we need to either have the sensors or the LED at the tip. So at the moment, that has some constraint. And I think it would lead to something a little different. You paint differently, and if the brushes we were measuring this and more like a paintbrush, it would. I think it leads to different, maybe different output, and we can do different. Interaction techniques with both, but one of the things that when we were running initial testing with this is how people grip it, and one of them ended up just picking it up and treating it as sort of a Chinese brush from the very top, and that felt surprisingly sort of comfortable to do, even with our prototype, even if it was not bending at the very tip, and we didn't sort of focus on this, but I think there's. It would be quite interesting to do. I don't quite know what the differences we would find, but I think bending in different directions would lead to both different interesting results. So, yeah.
Very good. Thank you very much.
Thank you.